Okay, welcome Tina and Victor and Alex and Donald and Aria and Warren. Thanks for coming. This is week 10. So we're getting close to the end, by the way. So pretty much we only have one more webinar after this one, by the way. So we're getting really close. The plan today is a couple things. One is I'll start out with questions or talking about the project. We have project 2 is due coming up this Sunday, and your draft is due on Thursday morning at 8 a.m. if you want me to look at it, or better is before, because if you wait till last minute, then it might take me a couple days to read, because there's usually a lot of these to read and they take time. So after talking a little about the project, we'll get into regression analysis. Regression analysis is really important. It's really the only major thing we do in the last half of the class that isn't hypothesis testing. Although we do one hypothesis test out of it, but the main piece is really working on understanding the relationship between two quantitative variables that might be linear related, might not, and if they are, what can we say about it? And how can we use one to predict the other? So that is the plan. A couple notes. One is, again, the project's due Sunday. And then next week is an off week. So it's a little different. In fact, this is the first time ever at our college we've taken the entire week of Thanksgiving off. But it's an off week, so there won't be a webinar next week. There won't be any assignments due next week. I'll still be checking my email on and off. Not on Thursday, though, because I'm doing Thanksgiving. But you guys probably are too. But we're really not going to have a webinar. We're not going to have any discussion posts, no assignments. Nothing is due next week. So that's just a note about the schedule. And then the following week, and then we get back into business. We just do a little chapter 13, and then we review for the final. So it's coming up. The final is definitely coming up. But don't expect me to be a little quieter next week, because I usually don't post anything next week because it's an off week. So let me ask you, are there any questions about the project? That could be from any of you. This is a good time. It's our last webinar before the project. So if you have questions, thoughts about it. So hopefully you remember I talked about the order at which you should write things. I talked about what should be in there. I don't have a page requirement, but there's a lot to write. So if you don't write it all, then I take off points. What I've learned about page requirements, if I do a page requirement, then people just write fluff to make it the right number of pages or whatever. So, but there's a lot of content requirement. And I've talked a lot about that already. The one requirement is to make sure that you copy and paste the part of your spreadsheet that has the test statistic, the confidence interval, and the p-value. Those columns, there's a couple columns that will have that. It'll either say dependent variable or independent variable, and that has to be directly into your project, or I take off a lot. So that is important to show that that you're using a spreadsheet. But I don't have a page requirement. Any other questions? Do you only want us to paste the one we used? I mean, don't just paste random stuff that you didn't use. So you're only going to have one spreadsheet. And so, for example, if you have independent data, then just paste the independent columns. Don't paste the dependent, because that's not relevant to your project. If you have dependent, then just paste the dependent data and not the independent statistics, because, again, you want to paste what's relevant. Does that make sense?
Perfect. That's exactly what I was asking, because I didn't want to have to paste the whole spreadsheet page when really only a small portion of it applied.
Right, but so the columns that say dependent or independent, whichever is relevant to your project, is what you should paste.
Okay, and not the raw data columns either, though, right?
Yeah, you don't need the raw data columns, because remember, this is, in fact, the name of the course is statistics. The name of the course is not data. So what's really important is the statistics, and the statistics that are important for this project are the standard error, the test statistic, the p-value, and the lower and upper bounds of the confidence interval. So those are the biggie. Yeah, and most of you use my spreadsheet because it's made for this, and that's what I'm talking about. It has to be if you're not using my spreadsheet, it has to be another spreadsheet. But again, I've made it just for this project, so I can't imagine you, and it's free. It's not like I'm charging you. So I don't know why you'd want to use something else. So it's again, it's two things. One, it's a proof that you use a spreadsheet because you're not allowed to use a calculator. And the other is then I can go and use it as reference to make sure that you're citing the right thing, right? Make sure you're reading the right stuff out of the spreadsheet. And as I've mentioned from the beginning, if you ever have questions, a project is a time where it's a big part of your grade and you can get as much help as you seek out. So I check a lot online. Interesting enough, between 4 and 8:30 a.m., that's usually when I'm really on a line. This morning, I didn't have any internet access, so I was missing that one. So if it took me a couple hours that you're not used to, I can get back to you until 9 a.m. Sorry about that. But at home, for some reason, my internet's down. So hopefully I get home and it's back. So I don't know what happened. So I think it was our street. So I'll apologize for that. But I'm going to be checking pretty much on and off throughout that time. My guess is Saturday or Sunday, I'm going to be doing a big hike. So there'll be 8 hours or so that during the daylight times when I'm not going to be checking because I'll be hiking. I tend to hike peaks and stuff. Okay, any other questions? Any other questions? Okay, and again, I recommend that you look at the project discussion forum and just read what other people have posted and what their questions were and what I replied about, so you can get an idea about what's working, what's not working, what are the common mistakes people are making, all of that. So definitely periodically take a look. I would say daily, take a look of the new stuff that's out there and you'll learn from it so that you don't make the mistakes other people have made the mistakes and at least I corrected. Okay, any other questions? Okay, so now what I want to do is I want to get to some regression analysis, and I want to actually show you something that was, in my opinion, and in most people's opinion, the most important application of regression analysis that has ever happened in my community. And I know, Arya, you're from my community, and there's probably a few others I'm trying to remember, but what is the most important thing that people look at scientifically in the Tahoe community? And while I post it up, see if you can guess. Okay, and by the way, it's obvious. Yeah, what about the environment? Something special about the environment? Water quality, but there is something special about quality. Not everything about quality, but one specific thing about quality. As soon as I show you, you'll all get it. Or at least those who live in Tahoe will. Color, you might have the idea. Yeah, Mark's got it. Lake clarity. Yeah, lake clarity or depth of clarity. And what I did, and this is like my favorite example because it's not just very relevant to what we're doing, but it's very relevant to Tahoe. This actually was shown to the President of the United States at the time when he came to Tahoe. So a trivia question, anyone know who the president was at the end? And that's why I've cut it off. That's about when he came. So end of the millennia. Yeah, Clinton. So Clinton came to Tahoe along with the head of Congress, and they learned about our clarity. And one of my statistics students was there when this was presented. She was actually serving them food. That was her job. She was working at the restaurant that they were having their meeting at, but still cool. And this was done by UC Davis. In fact, you can see a little boat that says UC Davis if you can't see it. And what they do is they measure the lake and the clarity of the lake with what's called a Secchi disk. And a Secchi disk is basically It's just a little white plate. That's all it is. And they tie it to a string and they let it go down until they can't see it anymore. And then they measure how deep it was by seeing how long that line was, that rope was that was connecting the Secchi disc. Okay, any questions on that? So again, if you're not from Tahoe, you now know what happens. And the cool thing is when they were, I was talking to the person in charge of this. I forgot what event, but it was some event. And he talked to me about this. If you look at each of these little discs, all these discs are data values, but they are not individual data values. I talked to him about it, and I asked him, what do these represent? And it turns out what these are is each year they do several measurements. Any guess on how many measurements they do? The hint is I just smiled so much when I heard the head of the scientific thing, group tell me about it. Yeah, they actually do 31. At least that's what he told me. And I didn't, he had never taken my class before. Probably took someone else's class. And they do 31. And the reason why they do 31, and hopefully you all know, why is it important that they do 31 and take the average of the 31 and call that the measurement? What does that guarantee? Yeah, it guarantees a normal distribution. So they use a central limit theorem, and then we know that these values come from a normal distribution because the values are, in this case, averages. Okay, in fact, they call that subsampling. I don't know if I've talked about that before, but this is called the subsampling technique, and it guarantees a normal distribution, which is something you really need for this to be able to do it right. Okay, most people do it wrong, by the way. All right, so now that we have all these data values, it's a whole lot of them, okay? The next thing we do is we look at this and we say, well, does this look like it follows a linear trend? What do you think? Does it follow a linear trend? Okay. Yeah, I like Alex's answer. It's somewhat but not perfect, and perfection you almost never get when you're doing data. But there's definitely look at it from the mid 60s, okay, or maybe late 60s to the late 90s. We can see we have a trend, okay? And in fact, I think I'm going to emphasize this, and I'm going to draw. Kind of a line. Okay, again, it's not perfect, but that's good enough. I just want to do eyeballing, and then we'll get into how do you actually calculate the equation of that and stuff like that, using a calculator, by the way. Okay, we can definitely see a line going through there. Okay, it's not perfect, it's definitely not. And in fact, if you look, for example, if we just follow a little area like over here in around 1983, 84, 85, you can see that actually isn't doing that line at all. But kind of generally, we get a linear trend. Any questions on that? All right. So one of the things, there's a bunch of things we want to look at. One is we want a measurement of how good the fit is. Okay, and we want a measurement that's going to do two things for us. And this measurement's called R. Okay, it's just the letter R. And anyone know what R stands for? Hint, hint, what's the title of this chapter? Yeah, regression. So R for regression. And it turns out that R is always a number between -1 and 1. And if it is negative, then the slope of the line is negative. And if it's positive, then the slope of the line is positive. Okay? So R is not the slope, but it carries the same sign as the slope. And if it's 0, then that line is horizontal. Okay? If the points are pretty close to the line, if we have a good fit, then it's going to be on the far side from 0. Whereas if it's a poor fit, it's on the close, it's closer to 0. What do you think? Do you think this is going to be far from 0 or close to 0? Yeah, this one's going to be far from 0. All right, now for a trick question. Do you think R will be positive or negative? All right, what you didn't pay attention to is what I said. This is a trick question. Take a look at the y-axis here. 40, 35, 30, 25, 20, 15. Do y'all see that? Okay. The way that UC Davis has portrayed this is that y is upside down. So it may look like a positive slope, but this is actually a negative slope line. Because as the date increases, the y values decrease because everything is tricked out. So I wouldn't do that to you on a test. But again, this is realistic. This is really important to Lake Tahoe, so I thought I'd use this as an example. Okay, do you see why this is actually a negative slope? So be careful and just always look at it carefully. All right, so we know this is negative, so let me tell you what R might be as a possibility. And again, I'm just eyeballing, that's all I want to do. So R, like 18. Is about equal to, it turns out it's a pretty good fit. So it's negative 0.95-ish. Any questions on that? Okay, the next big number that's important is what's called R squared. Okay, and I know mathematically it's not that deep, but it actually has a different relationship going on. So let me tell you what R squared is. First thing, I hope that you know how to pop that into your calculator. Okay, Alex is asking, is it positive 0.95? Again, this line looks like it's got a negative slope, but it's actually, I mean, a positive slope, it's actually the negative slope because y is upside down. Does that make sense, Alex? Okay, so it's negative, not positive 0.95. So why is it negative 0.95? Because it's got it, remember, it's on the far side from 0, and -1 is as far as you can get. Does that make sense? So it's pretty close to -1. It's not exactly -1 because if it was exactly -1, all the points would be exactly on that line, and they're not. Does that make sense at all? So if not, let me know. Yeah, I'm eyeballing it. We're going to learn in a bit at the end of this webinar, or maybe 2/3 of the way through. We'll talk about how you do it in a calculator. Okay, but these are a lot of points, and I didn't want to waste your time watching me put in, 30 points in a calculator. It would just take too long. So right now I'm eyeballing it. But again, when the points are really close, it's good to eyeball. It's important to be able to eyeball, to see that the points are pretty close to this line instead of scattered all over the place. Whereas if it looks like the night sky, okay, where the points are all over the place, then R is probably really close to 0, like 0.01 or -0.01. Okay, so it depends how it looks. Okay, R squared and I'll just go like that because it's kind of a pain to make a square out of this in paint. Well, that you should be able to do on your calculator. What's R squared? What's R squared? That you should all be able to tell me. If you know what R is, you should be able to tell me what R squared is. This is basic math, not even statistics, really. Yeah, and I'm going to round to 2 decimal places. So except, Tina, it's not negative. When you square a negative number, it's always positive. So R squared is equal to 0.90, or you can write it as 90%. And I like to write r squared as a percent because we can talk about what it means. Any questions on that so far? Okay, so r, we saw the fact that it's negative tells you have a negative slope line, even if it's tricky on this picture. The fact that it's close to 1, close to -1 in this case, tells you that the points are really close to the line. R squared is 90%. So what you can say is if we look at lake clarity, then there's been a variation. You'll see between, it looks like around, maybe 18 to 30 or so. And these are meters. And that's a pretty big variation, right? But if you just focus on a smaller time period, like just the last few years in the 80s, or maybe the first few years in the 70s, et cetera, and you look at the variation in a small time period, and you average that variation, then it'll be 90% less than what you started with as a variation. Okay, so Tina, if you put it up and got a negative number in your calculator, it means you forgot the parentheses around the negative. Then you want parenthesis negative 0.95, end the parenthesis, and then square it. Okay, so let me repeat what r squared is about. So the idea here is that there's a pretty big variation. If you just ignore the date and just look at the y values, they vary between, looks like around 18 meters to around 30 meters. Do you agree that's a pretty big variation? But if you just focus any particular few years, like say between 1972 and 1975, you only have maybe a year, a few meters of variation. If you look at the variation, and in particular standard deviation, it turns out, if you look at the standard deviation focused in small time intervals, and you average all those standard deviations, you'll get a 90% smaller average of standard deviations than if you looked at the standard deviation of all of the values. So that's what r squared is. I will let you know, and this is why, Victor, you're right to ask me to repeat it. This is the hardest concept of the entire chapter. So again, you'll have more chance to hear about it when you watch the long video, when you read the book, when you go and do the homework. But it is the toughest, for most people at least. Any questions about r squared in this case? Okay, we have a line, right? Hopefully y'all see a line. When you think of a line, what two numbers do you think about when you think of a line? What two important numbers happen in a line? And I want to look at those. So you got to think about algebra now, basic algebra. Good, the slope is one of them. And what's the other one? Yeah, the y-intercept is the other. Okay, so those are the two important numbers that you think about, that most people think about with a line. Here's the bad news, and Victor, I'm really glad you wrote it in words instead of letters. Don't write it in letters. Because on calculator, B is a slope. Sorry about that. And so is it on the spreadsheet. It's standard in statistics. So typically, the equation is first it's y hat, usually a hat's over the y, but I can't do that with the typing, is equal to a plus bx. So that's the first thing, is that we have y hat equals a plus bx. The reason why we call it y hat is it's the predicted value of y using the line, which is different than a data value of y. So for example, if we look at, say, 1984, the value of y for this data value looks like it's about 22, but the predicted value based on the line looks like 25. Does everyone see that? So there's a predicted value of y, that's y hat, and then there is a data value of y, and that's the y coordinate of the point that they've taken data from. And sometimes you can have more than one of those because you could have sometimes multiple points. In this case, you don't on the same x value. Any questions at all on this about this so far? All right, let's do the slope first. Who remembers how to find the slope of a line? Hoping a lot of you are saying, I do. When you think of 3 words I'm looking for, what 3 words do you think of? It's kind of a phrase. Don't go MS plus B. Remember, that'll confuse the hell out of you because B is our slope here. So definitely don't even ever say that in this class, or it'll just confuse you to death. So what is a slope in 3 words? This is something you all learn in like 7th grade. These coordinates, that's not 3 words, though. Remember? All right, if you're not telling me, rise over run. That's not familiar? I'm hoping you all hear that and say, oh yeah, that's slope. Okay, so don't forget the slope is a rise or a run, and I want to write that down. So slope, in this case, it's B. So again, you got to be real careful. So B is a rise over run. So now we got to see what is a rise, what is a run. So if we start, say in 1960, looks like about 1968 was probably the beginning, and that we're looking at 30. And then in 1990, it looks like 7. Let's call it 98 because it'll be easier. We're looking around 20 or so. So our slope is a rise. Well, we rose from 30 to 20, and that's a rise of -10. And then we ran however many years it had been from 1968 to 1998 is 30 years. And there's our slope. Any questions on that? Okay, how do you get the y-intercept? So how do you get the y-intercept? See if you can remember. And remember y-intercept. Okay, we definitely can't look at the line and see where it crosses the y-axis because the y-axis isn't on this picture. But we can get it. And if you don't remember it, let me remind you. Use the formula. Y minus y1, and your first value of y was 30, is equal to our slope, which is, by the way, -10 over 30 is -1/3, times x minus the x value for that value of 30, which is 1968. Any questions on that? Now, if we want the y-intercept, what can we plug in right away into this equation? It's been a while since this felt like a math class, but now we actually have a little bit of math to do. What can we plug in? If we want the y-intercept, what do we know? I don't see everyone jumping in at once. All right, maybe I'll say it. If you want the y-intercept, that means x is 0. That's the definition of the y-intercept. So if you plug in 0, then we get a -1/3 times 0 minus 1968, which is just 1968 over 3. So we can say is that our y-intercept equals 1968 over 3. And then we need to add 30 to both sides, plus 30. And you can put that in your calculator if you want. 1968 over 3 plus 30. And I get 686. Any questions so far? Oh, it didn't come out right. Sorry about that. Let me redo it. So the y-intercept is equal to 686. Why did you subtract from the year and not the value of the year? I'm not sure what you mean about, I'm not even sure it's value, but it's a visilu of for the year. So I'm not sure what you mean by that. Value. Not sure what you mean by value of the year. The value of the year for the y-intercept is just 0. Because it's y-intercept. And the x-axis is the year. Okay, 1968 is the year, and that's what we subtract. That's the x-coordinate. And for the y-intercept, x is 0. So maybe I'm not following what you're asking. So the y-intercept is when x is 0, and the 30 in the 1968 are the coordinates of the point, 1968 kind of 30, comma 30. The negative 1/3 was the slope. That's just the formula. Any questions on that? The x minus 1968? Yeah, well, I plugged in 0, and 0 minus 1968 is just negative 1968. Yeah. Yeah, 1968 is the value of x because it's the x coordinate is the year. All right, so now I want to start understanding the slope, and I want to think about what does the slope represent? So remember, because it says right here, the slope is a rise over the run. Okay? The rise is a change in the y coordinate. What does the y coordinate represent in this example? What's the y coordinate represent? Yeah, that's the number of meters that you can see that Secchi disk. Okay, so the rise is the change in the number of meters that you can see the Secchi disk. Okay, and by the way, our slope was negative 1/3. Okay, so maybe I'll even write that in to remind us that we can fix that. So our slope is negative 1/3. Okay. So what we can say, this is a fraction. And if you look at it this way, then you can say that we have risen negative 1 meters. And the run is the time elapsed. In this case, it's in years, so it's 3 years. Now, what does it mean to rise negative 1 meter? Yeah, it means it goes down a meter. So again, you want to say it sensibly. So what we can say is that for every 3 years, our clarity has gone down on average a meter. Any questions on that? And that is the interpretation of the slope. Okay. If instead of negative 1/3 you did as a decimal, then it's about 0.3. Then you would say 0.3 over 1, and then you would say that every year on average, we're losing 0.3 meters of clarity, which is exactly the same thing. All right, let's look at the y-intercept. Y-intercept is interesting. We want to interpret it. So what does it mean to have a y-intercept of 686? What was the value of x? 0. And what does 0 represent in this case? It's 0 what's? Okay, it's not 0 meters, because the 0 is an x value, not a y value. So what is it? Not 0 disks. Good try. Yeah, it's not quite 0 years. It's the year 0. We're in the year 2019 right now. And this is talking about the year 0. Any questions on that? Okay. Now the 686, what is that talking about? Yeah, that's meters of clarity. All right. So now this, you might have to live in Tahoe to know this. What would it mean for the depth of clarity to be 686 meters? Okay. All right. Well, here's the problem. I just typed it in Google, is that our lake is only 501 meters deep. Doesn't make any sense to be able to see 686 meters in a lake that is 501 meters deep. Okay. So that's one reason why this is nonsense. Let me tell you another reason why the nonsense. You never use a regression line to talk about a data value that is very far from the values that you collected. And I think you can see that the year 0 isn't anything like where we are now. Okay, none of these data values are anywhere close to the year 0. And in fact, what was the population of Lake Tahoe in the year 0? Anyone know? Yeah, it was 0. There were no people. You can't live here. There's no technology. You would die in the wintertime. Forget it. Okay. I know that, I don't know how many hundreds of years ago, there were some Native Americans that came in the summer. But if you want, the year 0, basically, it was a whole different place. We can't even talk about it. Any questions on that? So in this case, the y-intercept is not useful. If you think about the Donner Party, that was not the year 0. That was like something like 1,800 years later, or 1,850 years later. So not even close to year 0. Okay, so in this case, the y-intercept is pretty meaningless. One is because the x value is so far from any of the data values, we don't even want to talk about it. And the second, the y value makes no sense. So it's just meaningless, and that's okay. Any questions so far on what we've talked about? All right, here's the next question. Is how do we make a prediction based on this regression line of today's lake clarity? So how can we predict today's lake clarity using the regression line? Because really that's what you want to use the regression line for, is to make predictions. So what can we do? Let me ask you, and you better know the answer to this question. What year are we in right now? Good, good. 2019, that's one that you should all know the answer to. That's not our math question. Okay, that's our value of x, or is that the value of y? Yeah, that's the value of x. So what we can do is we can put it into the equation. So if you want to predict today's lake clarity, we can say A, and A was 686, because we already figured that out. And then you add the B, which is -1/3. So adding -1/3 is the same as -1/3. and then you multiply by x, which is 2019. And unfortunately, as soon as I let go, it's going to go away. So I need to do it there. There we go. Okay. Tell me what you get. Put in your calculator. Okay, yeah, about 13. Okay, 13 would be pretty horrible, by the way. 13 meters is a huge drop in lake clarity. Our lake would be murky and terrible. Okay, so here's the real story now. Okay, this is true history. Is that back in the late 90s, when Clinton and the heads of Congress are here, they saw this presentation, and unlike some other presidents that I've heard of, Clinton actually understood science and believed in it, and Clinton understood regression analysis, okay, what we're doing now. And he said, uh-oh, okay, and so did the Congress people that were there. And what they did is they said, well, we do not want the lake clarity to become only 13 meters by 2019. They probably weren't thinking about 2019, but in the future to be like just near 10 meters. That's not good, okay? So instead, what they did is they actually dealt with the lake clarity problem so that this trend would stop. Again, trends are not absolute. You know, you can't truly predict the future because things can change. And what changed is they passed a law and they brought in like $100 million to protect our lake. Okay, and let me just show you what it looks like now. It looks nothing like a 13 meter drop in lake clarity. Instead, got to reshare my desktop. Let me go find it. There it is. That one. There we go. Okay, so this is what really happened. So if you look at after Clinton came, Clinton came right around there. Then look what happened to lake clarity. If you just look at, I can't do that. If you just look at post 1996, what has the lake clarity done since then? What do you see? Yeah, it stabilized. And in fact, if you look at the regression line from 1996 till now, the slope is 0. Do you agree? The slope is pretty close to 0. So what do you think R squared might be if you look at post 1996? Any thought? Yeah, it's 0. Okay, which means that we've stopped the time progress, the horrible time progress that was happening. It still goes up and down. And again, you know, that is science, not statistics. And it goes up and down because of weather, climate. Climate does make things go up and down in terms of clarity. If you have a whole lot of snow in the winter, you're going to get a lot of runoff and things are going to go down. So the idea is R squared, again, tells you the percent drop in the variation if you just focus on one, you know, a little area of dates. So if we only look from 1968 to 1996, then we saw that was like a 90% drop in variation. The other 10% is due mostly to weather. Whereas if you look from 1996 to 2020 or 2019, the R squared is around 0, which means that looking at a certain year doesn't tell you anything about lake clarity because it goes up and down, but not up and down because of long periods of time elapsing. It goes up and down because of just short-term weather pattern. Does that make sense? Okay, so that is an example that has kind of all the important or most of the important information about regression analysis. What I haven't done yet, and that's what I want to do now, is I want to give you an example. We're actually going to calculate it, the R squared and R, and we're going to use our calculator to find A and B instead of just eyeball, because eyeballing is not the best way. But I did want to discuss, what's going on here. And eyeballing is important, but you also want to be able to do it using your calculator. My spreadsheet does it also. There's a regression tab, by the way, in case you don't have your calculator with you. All right, so let me reshare. And I need to get rid of all this because we're starting over again. That is, where's select? There it is. Okay, and now let me go. Let's go Canvas. That's better. And now let me pop in a question for you. You know what, it's too big. Just a minute. I need to make it smaller. I think that'll work. Still too big, sorry. Wonder what happened. Just throw it out. One more try. Make it really small. Let's see if that works. I think I know the problem. I'm sorry. I think the canvas is too small. All right, I may have to just tell you what the numbers are. Sorry about that. For some reason, the canvas is not showing up for me. See if that one does it. There we go, got it. Just canvas size. I apologize for that. It's gonna look pretty small. So I'm gonna read it out. So what it says is the data below show the results of a study of 9 community colleges done that looked at the percentage of students at the community college who receive financial aid and the percent who are business majors. Conduct a hypothesis test for the correlation and then perform a full regression analysis. Okay, so that's what we need to do, is we need to do a hypothesis test. All right, so the first thing what we're gonna do is, and hopefully you know this, How do you always start with a hypothesis test? Yeah, we need to write the null and alternative hypotheses. So that means H naught and H1. Okay, so H naught is always going to be the same for us, okay, in our class. So just let you know. All right, what letter is that? See if my handwriting is good enough. So, okay, it turns out it's not P. It's a trick question. It's actually rho. It's a Greek letter, and it's rho. And it's the Greek letter for R. And that's because we're thinking about regression analysis, correlation. And it's the population correlation. So the population correlation, rho, is equal to 0. And that's what H naught. So H naught is there is no correlation between financial aid recipient percents and business majors. Okay, and then H1. What do you think H1 is going to be? I'll start you off. It's rho. And then what's the next symbol going to be? Yeah, not equal to. Okay, and that's because if you have a correlation, then it's rho is not 0. Any questions on that so far? Okay, the next thing I'm going to do is I'm going to put this data into my calculator. So I need to do a new share. And there's the calculator. So what I'm going to do, when you're used to this, I'm going to get a stat. I'm going to get an edit. And then I'm going to clear out L2. I'm going to clear out L1. And in L1, I'll put the financial aid data, which is 42 and 38, 56, 19, 40, 37, 72, 55, and 20. And then for L2, that's the business major data. That was 15, 17, 7, 34, 12, 15, 6. Let's try that. Whoa, what just happened? Let's try that again. One more time. I think I was hitting shift instead of enter. 15, and then 17, and then 7, 34, and then 12, 15, 6, 9, 27. That's better. Okay, so you're used to doing this. Then we're going to go to stat. You're used to that also. And we're going to go to tests. Now we're towards the end of the class, which means we're at the bottom of the list, so use the up arrow. And the one we want is lin-reg t-test, because we're doing a hypothesis test. Okay, there is something called a confidence interval, but we're not doing that in this class. So we're going to do a lin-reg t-test, linear regression t-test. It turns out it's still t, just like a t-test before, but it's a special kind of t. I hit enter. Then the X list should be L1. The Y list should be L2. Freak is 1. We have rho not equal to 0, so I hit enter there. Don't worry about regeq. And then I hit calculate. And notice it does have y equals a plus bx. That's why you have to be really careful about that b, because it's not the y-intercept, it's the slope. And sorry about that. Don't shoot the messenger here. Okay. And then we have a t is -6 about. Is our p-value 5.02 about? Definitely not. Our p-value is 0.0000502. Let me write all this stuff down. So 0.00502. Notice it gives us A and B. A is about 37, I'm just going to call it. So we have 37 plus B is about -0.5. So 37 minus 0.5 x. And that's our y hat. Any questions on that? S we're not going to use, but R squared is 0.84. And R is about -0.92. Any questions so far? All right, so now we have everything from the calculator. I'm going to go back to the paint because I want to type out all our conclusions. That's what we've got. So let's go to new share. Let's go to our paint. Okay, our p-value is 0.000502. So what is the conclusion? And again, although you've never done a hypothesis test for a regression line before, I'm hoping you can tell me what the conclusion is because we've done enough hypothesis tests. That's too small. Let's make it bigger. Yeah, we reject the null hypothesis, and there is statistically significant evidence to conclude that there is a correlation between financial aid recipients, or the number of financial aid recipients, and the percent of business majors. Okay, actually, it's not the number, it's the percent of financial aid. Yeah, you could say strong if you want. It's definitely strong. You could brag about it, which is probably a good idea. Any questions on this? Any questions? All right, now we had that R squared was 0.84 or 84%. So now let's interpret that. So I want to write down all the interpretations. So let's interpret R squared. What we can say is that overall, there is a large variation in the percent of business majors from college to college. But if we only focused on colleges with a fixed percent of financial aid majors, then this variation will be decreased on average 84%. Any questions on that? Direct financial aid, focus on a fixed percentage of financial aid. Sorry, recipients. Thanks. Then this variation, okay, will be decreased on average by 84%. Any questions at all on interpreting R squared? That's the hardest part typically. Okay, let's interpret the slope. Okay, the slope was negative 0.5. We can write that as negative 0.5 over 1. And now, based on that, we can say okay, for every increase of 1% in financial aid recipients, the slope was about negative 0.5. That was from the calculator. Colleges tend, on average, to have a decrease of 0.5% or 0.5% business majors. Any questions on that? Okay, how about the y-intercept? Can the y-intercept be interpreted? What do you think? The y-intercept, by the way, was 37. So does it make sense to talk about the y-intercept here? Okay. Can you have 37% business majors at a college? Can that happen? What do you think? Can a college have 30% business majors? 37%? Unlikely, but it can happen actually. No, there's colleges. Business major is a biggie, especially for kind of private, expensive colleges. A lot of business majors. Can you have no financial aid recipients? Okay, it can happen, especially in these for-profit places. So it does make sense. So we can say is our best prediction for a college that has no financial aid recipients is that it will have 37% business majors. And it does make sense in this case. Okay. So I want to mention a bunch of things. One is these are predictions. They're general tendencies, averages. They're not causal. Okay. So let's say we wanted to say, what's our best prediction for a college that has, let's say 50% financial aid? How do you do that? So if I wanted to say for a 50% financial aid college, what's our best prediction for business majors? What will we do? Okay, we would put it into the equation. Y hat is equal to, again, our y-intercept is 37. Our slope was 0.5. And then we're putting in 50. Any questions on that? And that, by the way, is 12. I did that one in my head. Any questions on that idea? Okay, does that mean that if you looked at a college that had 50% of the students receiving financial aid, then that college will have 12% business majors? What do you think? Is that what this means? So if we look at a college that had 50% of its students on financial aid, then that college will have 12% of its students who are business majors. So tell me if that's what it means. What do you think? I don't see y'all jumping in, but I'm hoping y'all jump in. So Alex says, yeah. Anyone else? Tina says, yeah. Okay. All right. So I'm going to tell you it's a really good thing that we're not taking a vote, because the answer is absolutely no. And the reason why it's absolutely no is the word will. Okay. It's too strong a word. Regression analysis does not give you absolute numbers. Okay. Likely is not so great either. Predicted to is better. So let's write this down. So what we can say is our best prediction for a college which has, W-H-I-C-H, 50% of its students on financial aid is to have 12% business majors. Any questions on that? Okay, notice how it's different than saying that a college that has 50% of its students in financial aid will have 12% business majors. This is only a prediction. Okay, let me ask you another question. Based on this regression equation and all this work, if we went and decided to give more students financial aid, so for example, this year we have something called the Promise Program, and all of a sudden we have a whole lot more students on financial aid. Is that going to make it so that there are fewer business majors? What do you think? Right, we have a negative slope. So does that mean that giving students financial aid or more financial aid recipients at our college will cause a decrease in the number of business majors? Okay. Okay, and the answer is no. And you can't even say our best prediction. And here's a big, big no-no in regression analysis, and that's the word cause. Okay, and by the way, anything related to the cause, for example, you cannot say that, you know what, our business majors went down this year, and that's because we have more financial aid. You can't say that because because has the word cause in it. Does that make sense? So regression analysis never gives you cause and effect. Yeah, if you look at the slope, then we have all kinds of tendency on average to have a decrease. There's no causation here. Yeah, so correlation can never, ever give you causation. Causation only happens from science, never from statistics. Got it? Okay. An easier example to think about is there is a correlation between how many gray hairs a person has and their amount of money that they have to spend for healthcare. Do you agree with that? There's definitely a correlation between the two. Okay. Okay, someone with a lot of gray hairs is more likely to have a higher premium in their health insurance. Do you agree with that? Okay. All right, it can happen. I'm talking about an average, right? These are averages. Okay. Okay, there is a correlation, but here's the thing. There's no causation. So if I ask one of you who's, say, young, and I say, I want you to dye your hair gray, what you cannot say is, oh, I can't do that because then I got to spend more money on healthcare, because there's a correlation between gray hairs and money on healthcare, but it's not a causation. Making yourself gray is not going to cause you to spend more money on healthcare. Does that make sense? Okay, so causation and correlation should never be put together. And that includes any word that sounds like causation. That's a big deal. Okay, and I always test on that on the final. Okay, but I test it in a subtle way. So be reading, make sure you read for it. I don't just say, hey, does correlation mean causation? I'm gonna give you something, and gonna have you write something, and if you talk about the word cause with correlation, that's not good. Got it? Any questions on this example? So notice keywords here. Prediction is a typical word you use for correlation. That's fine. Okay, so in this case, R, that's a good question. R was negative 0.92. Let's put it over here somewhere. There it is. So R was equal to negative 0.92. But here's what that tells us. One is a negative. Negative C says as one goes up, the other tends to go down. As financial aid goes up, business major percent goes down, tends to go down. Any questions on that? And secondly, the 92 part says that the correlation is strong. Because it's far from zero. It's closer to -1 than it is to 0. Okay, and typically you use strong if it's more than 0.8 in absolute value. You'll use weak if it's like between 0.3 and 0.8, and under 0.3, usually just say none. No correlation. Okay, or weak to none, sometimes they'll say. Does that make sense, Victor? Okay, and that's what the R stands for. Good, I'm glad you've seen it before. Correlation, regression analysis is everywhere. Okay, you're gonna start seeing it in lots of places if you start looking. It's just all over the place. So this is a biggie. I told you this is a really important chapter. Okay, although we did one little hypothesis test, the rest of the stuff is more important actually. Whereas the other chapters, mostly we did hypothesis tests. other recent chapter, including the next one, by the way. So any questions about any of this? Okay, again, this is one example that I've written all out. We looked at another example. There's lots and lots of examples. Just a note, if we had instead a p-value of, let's say, 0.7, what would that tell us? Since, again, this is one example that had a small p-value. What if we had a higher p-value, like 0.7? Yeah, we fail to reject, and that tells you we don't have evidence to show there's a correlation. If we don't have evidence to show there's a correlation, then you shouldn't even continue. You don't even talk about the slope. You don't talk about the y-intercept, because if we don't have a correlation, the line is not useful. Got it? Okay, on the other hand, when you know you have a correlation, we can say the line is useful. Does that make sense? All right, I want to give you the secret word. How about in blue and bigger? And the secret word for today is the word you shouldn't use in correlation, and that's because. So I wanted you to remember that that's a kind of a forbidden word, is because. And that's our secret word of the day. So I've covered kind of all the details of regression analysis. Of course, I haven't gotten into lots of examples that you'll do as you do your homework. Okay. And I'm pretty much done with what I have to say. What I want to do now is take any questions. That could be about regression analysis, could be about your projects, could be about anything else too if you have another question. Let me stop the share to remind you that I can answer any questions you might have. So Tina, Victor, Alex, Lauren, and Mark. Let me know if you have any questions. I'll be happy to answer. Any questions?
Thank you, Larry. Have a good night.
All right, have a good night, Tina. Any other questions?
Thank you, Larry.
All right, thank you, Lauren. Victor, Alex, Mark, any questions? On the final exam, can we discuss if there is one, the correlation? So do you mean, are you allowed to discuss correlation in the final exam? If I ask you to discuss correlation, you definitely have to discuss it on the final. Is that what you mean? Okay, yeah, so definitely it could be on the final. I guarantee there will be a regression analysis problem on the final, because you haven't got one in the midterm, and if it's a big topic that you didn't get on the midterm, you get on the final. And we have this whole week on regression analysis, so that's a big topic. Okay, it'll look similar to the example I did. It won't be about, you know, business majors and financial aid. It'll be about something else. Let's see, we don't use alpha as 0.05. Typically with regression analysis, you could think about 0.05, but usually you talk about there is evidence, strong evidence, or weak evidence. And that 0.05 helps you break that down. Do you remember that? But if you're given correlation, usually 0.05 is what you use if you're doing a hypothesis test. But in our case, we had 0.000502, so it was clear, whatever alpha you use. Does that make sense, Alex? Okay, any other questions? Good question, though. All right, have a great night, Victor. Alex, any more questions? All right, have a good night. And for all of you who are watching this as an archived webinar, thanks for watching. And don't forget about your projects, due on Sunday, but hopefully you'll get me your rough draft in the next couple days is the best. And then I'll be able to read it and then give you lots of suggestions on how to improve it. So until then, have a great one. And we won't be having a webinar next week because that's Thanksgiving week. So the next webinar will be in 2 weeks, and that'll be the last one actually. So have a great week.